So this is in one particular state. Now, if we move over here, we see the qubit, where we have, and I've darkened the double bond so you can see them a little bit better, so that it's flipping back and forth between red and blue at 8 megahertz. Why 8 megahertz? I'll come to that in a second. But when the electron clouds are this way towards me, it's in the blue state. When they're that way, they're in the red state. Now notice the whole shape or size of the tubulin doesn't change, because we don't really need conformational changing of this magnitude as we've shown here. We just need a difference in states. Now in the Orch-OR model, we do need quantum superposition, but we've shown that the quantum superposition need only be a separation of the protein by the diameter of the carbon atomic nucleus, a Fermi length. So that's so insignificant and tiny you couldn't see it. But it's enough space-time separation to get the effect we need in the connection to space-time geometry. So this is the superposed qubit, and this is the 2010 version of the Orch-OR tubulin qubit, unveiled here tonight. And it's oscillating at 8 megahertz. Why 8 megahertz? That's a very good question. In their attack pieces, they did us a favor because they talked about these reports from a guy named Pokorny, who published in Bioelectrochemistry and other journals in 2004 and earlier. He measured, he was looking for coherence, for coherent excitations in microtubules and found them. He found that microtubules have a resonant frequency at 8.085 megahertz. So he was sweeping the frequency. When he got to this particular frequency, they changed their properties. It became very dynamic and active and radiated off energy. So this is their resonant frequency. And so we know they claimed that it wasn't quantum enough, that it wasn't like a Bose-Einstein condensate where everything is in one state, and therefore wasn't good enough for us. But actually even classical coherent excitations would be good enough for Orch-OR because the quantum is in the hydrophobic pocket. So they did us a favor by doing that. So we know that microtubules are oscillating at 8 megahertz and experimentally, and this is perfectly suitable, and we think it's driven by the London, the London forces, the van der Waals London forces in here. Now London forces cause attraction with nonpolar molecules by dipole dispersion, but when they get close together, the repulsive forces are 100 times stronger. So they go together and they spring apart like that, which means they're going to, as they do this, they're going to couple to acousto-conformational resonances, which could lead to propagation of information and vibrations around these particular lattices in the microtubule. The microtubule structure is very interesting. This is the thing that really interested Roger Penrose when I first told him about microtubules. If you follow any particular lattice pattern around, it repeats at, in this case, 3, 5, 8, and 13, 21, the Fibonacci series. It's got this elegant geometry, which it turns out is conducive to what's known as topological quantum error correction. So topological quantum error correction leads to the hybrid version of the 2010 tubulin qubit. So if we start from this qubit and we line up over here the nonpolar electron resonance groups, we find the 3 start, the 5 start, the 8 start, and the longitudinal protofilament lattice pattern here. So these could be topological qubits. So instead of having each tubulin being in one or the other or both states, we can have these pathways represent the information, the bit or the qubit. So here are the possible pathways. There are actually many of them, and they can be all mixed up. And here's a superposition of all of them. Now, if you do it this way, you lose the total capacity for information processing because you need many tubulins for each qubit. But you gain tremendously in terms of resistance to decoherence, because if one of these guys gets knocked out of coherence, it'll get pulled back in by the resonance of its neighbors. So this is topological quantum error correction, which stabilizes the quantum state of the microtubules long enough to reach threshold for self-collapse in a moment of consciousness, according to Rogers' equation, E equals h over t. So this is the topological qubit. So in summary, let me just back up and point to the conclusions here, that the tubulin bit and qubit in Orch-OR switches due to these collective actions of the van der Waals London forces in these hydrophobic pockets, which is where anesthetic gases act. And there's good evidence now that anesthetics bind to tubulin in neurons at clinically relevant concentrations, and gene expression following anesthetic exposure for tubulin is increased. So although most of the attention has been paid to GABA receptors and acetylcholine and a few others, actually it's more likely that anesthetics act on microtubules because they have so many sites, and because microtubules are sensitive to these London forces, which are going to be blocked by the anesthetics, and because this is where consciousness is, and ultimately anesthesia affects, erases consciousness selectively, allowing other functions to continue. The synchronized switching is due to the Froehlich coherence through the London forces. These guys, McKemish et al., they present their own tubulin model, their own version of a tubulin bit based on a single conformational switch driven by GTP hydrolysis. They completely ignore the London force proposal we've put forth for many, many years. They assert incorrectly that switching in the Orch-OR bit qubit depends on irreversible GTP hydrolysis conformational change. They then easily disprove their own ridiculous tubulin bit and assert they have disproven Orch-OR. There's new findings in quantum biology of warm quantum coherence. There's very exciting news suggesting quantum states in microtubules. Orch-OR remains viable, testable, and the most complete theory of consciousness yet proposed. And the Australian people missed the boat entirely. So I invite them to this meeting to debate with me, to have a session. They chickened out. See you next time.